Hey guys, it's Monday, September 28th, and today's topic is 2.7 mixtures. So, we started talking last week about matter and how everything that has volume and takes up space is matter. And then we talked about pure substances being a classification or a subcategory of of matter. And then we subclassed pure substances into compounds and elements. Well, today we are going to be discussing the other side, the other category of matter, which is mixtures, 2.7. Here you have lemonade, and the reason why they're showing you this lemonade is because lemonade is considered a mixture. It's a combination of water, lemon juice, and sugar. Now, they take into account that they remind you that it's not an element because it's made of more than one substance. And then they ask us whether it's a compound. Well, the main reason that it is not a compound because it is chemically not combined. It is just mixed in. So let's go ahead and ask ourselves, what is a mixture? A mixture is a combination of two or more substances in any proportion. This is different from a compound because we know that compounds have a fixed proportion. If we want to deal with water and in order for us to deal with water, there has to be two hydrogens and one oxygen. If we change the proportions, we change the compound. And since a mixture can be any proportion, it cannot be a compound. A the substances in a mixture do not combine chemically. That's also a reason why it's not a compound. Compounds are bonded chemically at the molecular level. Mixtures basically intermingle and keep their original physical properties. Okay. And some proportions that we could change is we could add more or less lemon juice, or we can add more or less sugar, depending, or we can even not use sugar and use a fake sugar known as aspartame. What are some other examples of mixtures? Other examples of liquid mixtures can be salad dressing and salt water. Okay. If you are looking for examples in the form of a gas, well, the air inside of your room is mainly nitrogen and oxygen. You got some carbon dioxide in there and probably some other type of gases. If you're looking for a solid example of a mixture, you can take into account granite. Granite is usually made up of a wide variety of minerals, just like you see in this picture. This is an example of a rock that is a mixture of small rocks and minerals. So let's categorize. Mixtures can be further categorized into a homogeneous mixture or a heterogeneous mixture. For example, the lemonade in the opening picture is an example of a homogeneous mixture. A homogeneous mixture has the same composition throughout. Think of it. Remember when we talked about uniform? If it looks uniform, like one color, it's going to be homogeneous. Okay, so here it's all one color. In this case, a light pink, a light yellow color. That is a homogeneous mixture because it's all one color. If we were to take into consideration the rock, that would be known as a heterogeneous mixture because it varies in composition. You can see that there are dark areas, there are light brown areas, and there's even some white areas. Okay. Um, Now, for mixtures, you can have different properties depending on the size of the particles.
Hi, it's Mr. Dool, and today we're going to be talking about types of mixtures, starting with a quick review of classifying matter. So matter can be broken into two different parts, and then further broken down from there. The first part would be pure substances. That's where we see elements. It's also where we see compounds. The other side of matter that we don't really talk about a lot, until of course we get to the solutions unit, would be mixtures. And we also see two subcategories in mixtures, homogeneous or homogeneous, and heterogeneous. So you can have a homogeneous mixture, you can have a heterogeneous mixture. So this is really where we're going to be focusing in this screencast today. We're starting with heterogeneous mixtures. Those don't blend smoothly throughout. So when you're looking at a heterogeneous mixture, you can see the different components in it. So that's why it says this: the individual substances remain distinct, because you can see the dispersing particles, you can see the dispersing medium. So it's very easy for you to tell just with your naked eye whether or not a mixture is heterogeneous. So if we're starting with the largest particle size, I'm only going to talk about three of the major categories of mixtures today. That's going to be suspensions, colloids, and solutions. Suspensions is where we start because it has the largest particle size. So this is a mixture where if you leave it, the particles that are dispersed in this mixture are going to start to settle out. So we see this most commonly in Italian dressing. We can also see it in the pharmaceutical world. I worked in a pharmacy for 7 years. Very often, we'd have to mix up antibiotics, in this case amoxicillin, but several different medications that a pharmacy will dispense are suspensions. And so they have to be added to water just prior to dispensing it to the patient, and then have to be reshaken before the patient actually takes the medication. So those are good examples of suspensions. In fact, I don't know if you can see this, but the label right on here says suspension. So there it is. The next thing would be a colloid. A colloid is a mixture containing mid-sized particles. So the particles in colloids are smaller than those in suspensions, but they don't settle out. So that's the major distinction between suspensions and colloids, is that in suspensions you see the particles begin to settle out. In colloids, that just doesn't happen. Colloids are tougher to see. In fact, in some cases are impossible to see with the naked eye. You can't really necessarily see the particles unless you shine light through it, but we'll get to that in a second. Good examples of colloids would be milk. Milk is something that most people have in their fridge. Those are colloids. Can't really see individual particles within milk, right? It looks very uniform. However, it's technically a heterogeneous mixture. But also, this is my deodorant of choice if you're going with it. An aerosol would be Old Spice Fiji. So as this sprays out, that would also be considered a colloid. Okay. Now, if we slide further down the particle size scale, we get into the homogeneous or homogeneous mixture realm, and this is where it contains substances that are fully blended. Now, I want to make an important distinction here. Blended does not mean bonded. So when I'm making a solution or I'm making a homogeneous mixture, I am not encountering a chemical reaction. This is a physical change, not a chemical change. So homogeneous mixtures appear fully blended, but chemically you can still separate these out. However, you can't tell the difference between the substances. So solutions contain the smallest particle size. Those would be atoms, ions, or molecules, and they're fully dissolved. So my favorite example for this would be Kool-Aid. Scratch that. My favorite example would definitely be coffee. Coffee is a solution. But Kool-Aid is a lab that we do in class where we make different types of Kool-Aid, and we talk about the concentration, solutions, and saturation, and those sorts of things. So I've got a fake beaker here, and I'm going to fill it with water. In solutions, we have particular terms for this dispersing particle and dispersing medium that I've been talking about. For instance, the solvent in a solution is what we call the dissolving medium. So in this beaker of water here, the solvent would be the water in the beaker. It's not till we get to the stuff that we're actually dissolving that we call a solute. So I have just some random, this is an atom, ion, or molecule here. That would be our solute for this situation. So when I add the solute to the solvent, it's very dramatic, and those mix, I now have a solution, but I also can't really see that particle anymore. So take a look at your screen. See that particle anywhere? No, it's completely mixed. So like I said, a good example of this would be coffee, which is delicious. This is also arguable because a lot of people say, oh, hey, what about coffee grounds in the coffee? You're right, that would technically be a suspension. But I'm talking pure coffee, that would be a solution. So then we get to this notion of, all right, so what's the difference between colloids and solution? If colloids, the particles in colloids don't settle out, then how is that any different from solutions apart from the particle size? And this is where we get to the Tyndall effect. The Tyndall effect is talking about what happens when we shine light through a colloid versus a solution, or really any type of mixture. You can test this on. So I have 2 glasses of water here, and they're different mixtures. One is a colloid, so obviously this one is a colloid, and this one is a solution. So they really don't look very different at all. But when we take laser pointers, I have a laser pointer at the left of each glass here, and I shine the laser through the colloid, what I see, change my color here, what I see is this. I actually can see the light in this mixture, which is how I know it's a colloid. So what is that analogous situation in a solution? Well, I shine the light through a solution, and I don't see that light in there. So maybe thinking, well, why does this happen? This happens because the particle size of colloids, the particles are bigger. Particles are bigger. So what happens is as this light is shining through the mixture here, the light is actually scattering, which makes it visible to us. Here, the particle size is so small, we're talking atoms, ions, molecules, that there's not enough particle in the way, if you will, to scatter that light. So we end up not seeing anything at all. So that's a little bit about type.
All right, so solution suspensions and colloids are all types of mixtures. Mostly it's all about the particle size that's the difference, okay? And here we're talking about first solutions. They give us an example of salty water. It's homogeneous. It has tiny particles. The particles are way too small to be seen or to settle, and they usually do not get filtered out. When it comes to a colloid like Jello is also a homogeneous mixture, but the size of the particles have now changed to medium. So particles are maybe a little large enough to see, but not large enough to be filtered out as well. Our last example of a suspension is Italian dressing. Italian dressing is where we completely change to a heterogeneous mixture with large particles. These particles you can definitely see with a naked eye and can be or will settle at the bottom and can be filtered out. Okay. So let's say if you're going to a paint store to buy a can of paint, usually sometimes the employees will ask if you want it to be shaken. Basically, the paint will not scatter. I'm sorry. The paint will settle out. So to make sure that the color is uniform, you want to shake that can of paint before you take it out of the store, because that is considered a suspension. If you go to the supermarket, HEB or Walmart, excuse me, and you buy milk, milk is gone through a process known as homogenization. They take thick cream and break it up into smaller pieces or smaller particles so that it can easily sit on a shelf for a while and not look all clumpy when you open it. Another example of a colloid is this milk that we're talking about. Separating mixtures. When you're trying to separate or get a component out of a mixture, there are a couple ways that you can do it. You have to think in terms of the physical property of the substance you're trying to get back. taken to a point, boiling point, melting point, ability to dissolve, and the actual size of the particles. Okay, and you could use these physical properties and to get back the original component by boiling, dissolving, or filtering, or all three. Here we have a picture of the Great Salt Lake in Utah. Obviously, you can see that the shore has white salt deposits. Now, why do you see that? Is because every time it rains, that level of water will increase. And since Utah is really, really close to the desert, it can get really, really hot at times. Obviously, evaporating some of the water, and since it is a mixture of salt and water, that'll leave salt behind, and that's why you see such a white shore instead of brown. And the reason is because water has a lower boiling point than salt, so it would not evaporate like the water does. If you have a mixture of salt and pepper and you want to isolate the salt away from the pepper, you can use you can first dissolve the mixture, all of it, the salt and the pepper, in water, and then use a filter paper to separate the pepper from the water and the salt, and then boil off the water and leave whatever's left of our salt mixture. Okay, that's just a one way you can use physical properties to get a component of a mixture back. So in summary, a mixture is a combination of two or more substances in any proportions. The substances in a mixture do not combine chemically, so they do retain their own physical properties. Homogeneous mixtures will look uniform or one color. Heterogeneous mixtures will vary in composition, or you'll see multiple textures, multiple colors. Mixtures can be classified on the basis of particle size. Solutions have tiny particles. Molecular, you can even say it at the molecular level. Colloids will have medium-sized particles, and suspensions will have very large particles. Okay, if you want to gain back a component of a mixture, you can use physical properties to filter, boil, or to physically separate. Your review questions are due. Make sure you send them as soon as you're done. Thanks, guys.